A standard calendar application works perfectly for 10 users, but introduce the erratic, high-volume traffic of a distributed enterprise network, and those applications immediately shatter. To understand why, we are analyzing the Events module of Project NEXUS, specifically version 1.5.0. At its baseline, this system handles standard CRUD operations. It creates events, categorizes them, and executes have-seen formula calculations for near-me radius searches across a distributed network of communities. But those features are just standard application logic. The true stress tests occur when the system handles thousands of simultaneous RSVP requests, processes infinitely repeating calendar loops, and manages asynchronous scheduled cron jobs without duplicating data. Scaling a system to meet these demands does not require provisioning massive server compute power. The solution lies in designing strict mathematical constraints across 8 foundational database tables. We will deconstruct how NEXUS prevents race conditions, database bloat, and duplicate job execution using concurrency control, bounded temporal logic, and idempotent state machines. Building a resilient event engine is an exercise in relational database architecture. Consider a highly anticipated community event with a strict capacity limit of 100 attendees. The database currently records 99 confirmed RSVPs. This split-lane timeline illustrates the naive engineering approach. The application executes a standard select count query against the event RSVPs table to verify available space. At the exact same millisecond, 2 requests, user A and user B, arrive. Because both queries read simultaneously, both register the capacity as 99. Both satisfy the limit logic and execute an insert. The database writes both records, pushing the capacity to 101 out of 100. You cannot solve a millisecond overlap with application-level code. By the time the code executes, the data is already stale. The enforcement must happen at the database tier. Here is the event RSVPs table schema. NEXUS prevents the overlap by utilizing pessimistic locking, specifically the select for update SQL command. When user A's query hits the target row, the database applies an exclusive lock. User B's transaction is forced to wait in a queue. It cannot read until user A finishes processing, increments to 100, and releases the lock. When the lock is released, user B's transaction finally reads the data. It now correctly sees the capacity at 100. The RSVP fails the availability check. Instead of dropping user B entirely, the system initiates an automated shift, routing the rejected request into the event waitlist table. To assign a queue position without triggering another race condition, the system executes an isolated insert statement. It calculates user B's spot dynamically by querying the maximum current position and adding 1. Implementing pessimistic locks transfers the burden of capacity enforcement from the application to the database. The result guarantees mathematical exactness and completely eliminates race conditions under high load. The second architectural challenge involves recurring time. Translating a human concept like every Tuesday and Thursday into distinct, queryable database records requires structural compromises. A common flawed approach is storing a single iCal recurrence rule string in the database and relying on the application to calculate all future occurrence dates on the fly every time a user requests the calendar. Read time calculation degrades our backend performance severely. If a user executes a geospatial near-me search, the system must unpack and calculate recurrence rules for thousands of events in real time before it can even begin filtering by location. The alternative is write-time generation, executing the logic once upon creation and generating individual database records for every future occurrence. This visual represents the fatal flaw of unbounded write-time logic. If a user sets an event to repeat daily, forever, the system enters an infinite while loop, infinitely multiplying records until it crashes the database. To maintain query performance without crashing the database, NEXUS employs bounded temporal instantiation. This diagram illustrates the template pattern. The original event is saved in the events table with an isRecurring template flag set to true. It acts as a parent node, spawning discrete child occurrences linked back via a parent event ID. The backend logic contains strict limits on how many child nodes can be instantiated. The bounds are explicit. The system will generate a maximum of 52 occurrences or project a timeline exactly 1 year into the future. Once either limit is reached, instantiation stops. Generating discrete records allows users to mutate specific moments in time. An organizer can cancel a single week's meeting, and the system only needs to update that specific child record, leaving the parent template and all other occurrences intact. Enforcing strict temporal bounds at generation trades the illusion of an infinite calendar for highly performant, queryable, and mutable data. The final architectural hurdle lies in the event reminder service, which manages 24-hour and 1-hour pre-event notifications via asynchronous cron jobs. The system operates on a pull mechanism. A script executes every few minutes, calculates a time window of 60 minutes, multiplied by the hours remaining, plus or minus a 30-minute buffer, and searches for matching events. This diagram shows the failure state of distributed cron jobs. Server lags, network timeouts, or redundant server instances can cause two identical processes, cron A and cron B, to wake up simultaneously, querying the exact same list of attendees. Consequently, attendees receive duplicate, identical email reminders. Resolving this requires decoupling the timing of the cron job from the execution state of the email dispatch. Nexus achieves this by building an idempotent state machine, utilizing the event reminder sent table. Looking at the event reminder sent schema, the entire mechanism relies on a single database constraint, a 4-part composite unique index covering the tenant ID, event ID, user ID, and reminder type. Before dispatching an email, the application attempts an insert-ignore command using this exact composite key. Cron A writes the key and sends the notification. Milliseconds later, cron B attempts the identical insert, but is rejected by the constraint. Because the database physically rejects the redundant insert, the application reads the rejection and safely drops the duplicate task without sending a second email. Utilizing a database-level composite index ensures that a specific notification is sent exactly once. The asynchronous email system becomes immune to cron overlaps and failures. Stepping back from individual table mechanics reveals the macro design of the Project NEXUS ecosystem. This architectural map demonstrates how the core events module connects outward. Because capacity limits are mathematically locked and asynchronous states are idempotent, the engine safely shares its state across external modules and federated tenant boundaries. Through the isFederated flag and the source tenant ID column, users from entirely separate communities can browse and RSVP to events across the network without risking data corruption. This reliability is fully realized in the event attendance table's direct integration with the platform's Timebanking wallet. Because the data integrity of the attendee list is secure, the act of checking into an event executes higher-order logic. An organizer marking a user as attended automatically calculates the hours credited and triggers a secure financial ledger transaction, transferring time credits directly from the organizer's wallet to the attendee. Backend architecture relies on designing unbreakable database constraints. By moving the logic from the application down to the structural tier, you render edge cases mathematically impossible.